Welcome back. Let's continue with our next session. Get ready to delve into the intricate world of vector search algorithms with our next speaker. Just a second. I miss it. With our next speaker, Dusan Milunovic. He's at the forefront of unraveling the mysteries behind these keys algorithms powering AI-driven searches. He's a data engineer at SmartCat, who is our silver partner, and we would like to thank you for your support all these years. In his talk, Under the Hood, Key Algorithms Powering Vector Search, Dusan will dissect the crucial algorithms like HNSW, LSH, and PQ, providing a concise yet comprehensive understanding of their role in AI-based searches. With a passion for data-intensive challenges, his expertise spans machine learning and data engineering, offering a unique perspective on the technical intricacies fueling vector databases. Please, Dusan, the stage is yours.
Thank you for the introduction. As she has already said, today we'll be taking a peek under the hood in the terms of vector search. So, why is this a relevant topic right now? I'm sure you've all been hearing a bunch about LLMs, you've all been using them, hopefully. And so, one thing that LLMs and machine learning models in general do is they represent data as vectors. And so, if we imagine a case where we've got, let's say, a website serving cooking recipes, an LLM can represent each of our recipe as a vector in an n-dimensional space. And then, when we want to do a semantic search of these recipes, we can also turn the query text into a vector and find the most similar vectors, and that should be recipes that are similar to our search. So let's say we've got a bunch of recipes, we try to search for butter chicken, it should find us similar recipes with similar words in their title or text. So we're not doing exact match search or keyword search, we're doing semantic search. And how does that look? Here on the picture, we have our database, and that's the 6 blue two-dimensional vectors. Now, in reality, we often have millions or even billions of vectors, so this is a really small 2D use case. Again, in reality, we're often working with much larger vectors, so 1,000 dimensions or something. But this is really easy to showcase like this. And what our issue is, or the problem we're trying to solve, we get a query, we vectorize it, that's the red vector, and we try to find n, that can be 10 or 15 or whatever, most similar vectors to it. And that's our results. So that is the core issue that each vector database has to solve. And this is just one of them, but I would say it's the core issue. You've also got to solve replication, sharding, like high availability and stuff like that. But this is what we'll be focusing today. Okay, so how do we solve this? It's really easy, right? You just have to give your query vector, use a for loop, decide which measurement of similarity or distance you're using. That's usually cosine similarity, and you compare your query vector to each other vector in your database. So pretty simple, works, right? Now, imagine a case where you're Google and you're trying to index as many web pages as possible. Each of those pages gets vectorized to a large dimensional vector. You can't really store this in memory, and linear search just isn't going to cut it at that scale. So we have to be smarter than that. And the solution, the same as in relational databases or any other type of database, is to use indexes. Now, what's an index? It's usually a data structure plus the algorithms that go with it to efficiently search our base. So here, our base are vectors. And in this context, there are 4 relevant type of indexes. So hash-based, tree-based, graph-based, and inverted file indexes. Today, we'll be covering LSH, which is a hash-based algorithm, and HNSW, which is a graph-based. Tree-based and inverted file indexes, tree-based are similar to graph-based, and inverted file is actually similar to hash-based. So there's not much point in going too wide here. One more technique we'll be talking about, so it's not an index, it's a technique to save memory, to store vectors more concisely, is product quantization. So that's not here on the image, as it's not an index, it can be combined with different types of indexes. Let's get into locality-sensitive hashing. So whoever has done any programming ever knows what hashing is. We've got some inputs, in this case, vectors. Usually it's texts or objects. And we want to hash them to a unique value. So that's what our mathematical function is trying to do, to hash it to a unique number or string or whatever. What we're doing here is the opposite. So we're not trying to get unique values on the output. What we're trying to do is if we have a couple of vectors that are all similar, so close to each other, we're trying to hash them to the same value. And we'll see the point of that. But let's first start off with an example. So this is our database. We've got these 6 vectors. Again, we're using 2D vectors as it's easy to show. In practice, we're going to be using much more dimensions, but you can't really show that. And what we do is we add a hyperplane. So in 2D, that's a line. In 3D, that's a plane. In more D, that's a hyperplane. And what it does basically is split the space into 2 parts. And we say, okay, we're going to encode our vectors using this hyperplane. Everything that's left of it or up, so in the blue space, it's a 0. Everything that's in the orange space, it's a 1. And so the result is B, E, C, A, they've gotten their encoding as 0, and D and F, they've got 1s. We repeat this process n times. So once again, we've split the space with a different hyperplane. These hyperplanes are randomly generated. And so B and D now get 0s, C, A, D, F get 1s, and we concatenate these values. So in the table below, you can see that B and D have the same hash value, and that's exactly what we wanted. So they're close to each other, C and A, D and F. Now this isn't perfect, obviously, but what it does now, so this is the result. We've split our space into 4 smaller subspaces. And what it does, when we get a query vector, the red vector, in order to find the most similar vectors to it, we just search that subspace. So we first have to compare it to these hyperplanes, see that it belongs to the green subspace, and then we only compare it to C and A. And that's how we cut down our search space, right? Okay, that's practically it for LSH. So some things to consider here. How many hyperplanes do we use? Obviously, the more we use, the more granular our space is divided. And one more thing to consider is data distribution. So if you look at this image, we could easily imagine that all of our vectors are in the top left corner. They're all in the blue subspace. And then if we get a query in the green vector, there's nothing to compare it with, right? And if it's in the blue subspace, then we compare it with everything. So we've just made the issue worse, right? So those are the 2 big things to consider. One way to mitigate this issue is not to search only our space, but the neighboring spaces as well. So if we get a query in the green, we could search blue and orange spaces as well. Anyhow, I think that LSH, it's a really simple algorithm. It really showcases well what we're trying to do, and that's why I chose to present it. But in reality, it's not used all that much since it's got a bunch. These fine-tuning issues, they're not easy to solve. Okay, next topic is product quantization. So I've already mentioned it. Quantization in general, it's used a bunch in machine learning models. The point of quantization is to take our values. In this case, these are vectors, high-dimensional vectors. And their values are usually represented as float 32s or float 64s. And what we're trying to do is use a simpler data type to represent these values. So ideally, integer 8 or integer 4, which take 1 byte or half a byte instead of 4 bytes for a float 32. Okay, again, we'll be going through an example. In this case, I picked to have 3 vectors. They're all 6-dimensional. So 6D is not something that we can easily show in a 2-dimensional or 3-dimensional space. But the first step of this algorithm is to split the vectors into smaller chunks or segments. The next step is to train some model to, instead of using the original values, it's supposed to learn how to use values from the simpler data types, so ints, to represent these segments. Then we encode the vectors, and the last part is how do we query the encoded vectors. Okay, so let's start off with splitting. We'll be splitting these vectors into 3 segments, and each of these segments will be looked at separately moving forward. So keep that in mind. We're splitting it into first, second, and third. And the next step is now for each segment to train a model on how to represent them as simpler data types. How do we do this? Let's take a look at the first segment. So now we've got 2D segments, and this is something we can show in a coordinate system that's 2D. And these are the values for vectors A and B, and the C is down. So when we do, here we're using clusterization to just, and we're going to use 2 clusters for this example, and we're just gonna let the algorithm decide which points or vectors belong to the same clusters. And this is a result. This visualization is a bit off, but I think it gets the point across, and that is that segment 0 of A and B are the same cluster, and segment 0 of C is another cluster. We now add IDs to these clusters, and the result is A and B get ID 0, C gets ID 1. We repeat this process, so the whole training process and encoding process for the following, for all segments. And in the end, this is what we get for our vectors. So we started off with 6 values of float 32. We end up with 3 values of, these are practically Boolean values. You can use 1 bit, but that's not actually practical. You're usually using int 8. Okay, so now let's talk about what we can do with these vectors next, because now we've got encoded vectors. And if we have a case like this one, so in this case we use 3 centroids or 3 clusters per segment. And if we look at these 3 vectors, this is their encodings, it would seem to us that A and B are more similar to each other than A and C, because 0 is more similar to 1 than it is to 2, right? But in reality, these are just cluster IDs. They could be all over the place. We don't know anything about distances between cluster centers. So what we need is to keep another data structure, and that's a code book. And a code book, practically, it just remembers for each cluster where its centroid was in that 2D space. So this is an example of a code book. In this one, we've got 3 clusters, right? So each cluster only has 1 vector. But down there, you can see for segment 0, we're keeping a code book, which is coordinates of centroid 0, coordinates of centroid 1 and 2. And for each segment, we have to do that. Now, we can decode our vectors using this code book. So if we want to decode vector A, all we need to do is see that it's got cluster 0, 0, 0, and take the first row from each code book, right? Because that's cluster 0. And this is vector A decoded. Now, obviously, this is not the original value of vector A, so we're losing something here, but that's the price we've agreed to pay, right? So we're not doing total precision. The same is for every one of these indexes. Okay, so how do we now query these encoded vectors? What we could do with everything we've done, talked about so far, we could decode each vector from our database and just compare them to the query. So we would get a bunch of 6D vectors in our database and a query, which is also a 6D vector, just compare them. But in that case, we've not accomplished anything. All we've done is encoded, decoded, lost precision, and now we're doing comparison. We've wasted time and resources. So one way to do it is to turn the logic around. So we're not going to be decoding our database vectors. We're going to be encoding our query vector. And practically when we get a query, we encode it. We get centroid IDs or cluster IDs. And we keep another data structure that remembers for each segment the distances between cluster centroids. And this is it. And so now we can see for segment 0, clusters 0 and 1 are 1.5 units apart. Clusters 0 and 2 are 1.1 units apart, whatever the unit is. And when we want to compare some vectors, you go segment by segment and you just look up the distances from this table. So for segment 0, if we compare C and A, we can see that that's the distance between cluster 2 and cluster 0. We just do the lookup in the table, we get the red value, which is 1.1, and C and B, their distance for segment 0 is 2.3. So as I've said, even though it looks to us like A and B are more similar, when we decode them back, we can see that they're actually further apart from each other. That would be it for product quantization. Some things to consider here is how many segments do we use and how many centroids per segment do we use. Now that's the limiting part. If we want to use more than 256 segments per centroid, we're going to need a larger data type since integer 8 only fits 256 values, right? And of course, the more segments, the more precise you keep your values. And now let's just take a look at an example of how much memory can this save us. So this is, in my head, mind-blowing. We've got an example. We've got 1 million vectors. Their dimensionality is 1024. Their type is float32. This is my mistake with the int. And to keep that in memory, it would take us 3.8 gigabytes of memory. Now this is for 1 million vectors, and as I've said, we're often working with tens of millions or billions or tens of billions data points, so this isn't feasible at all. With product quantization, with 16 segments and 256 centroids per segment, you need 16 megabytes, or maybe a bit over that, top 17 megabytes. This is now over 2,000 times less, right? This is practically nothing. You can dream about keeping billions of your vectors in your memory. And one thing we'll see later is that you can combine PQ with indexes, so you get both memory consumption and speed gains. The last index now that we'll be talking about is HNSW, Hierarchical Navigable Small Worlds. And so this is currently the best index that there is. Every vector database uses it by default. And so that's why we're going to talk about it. It's also really a fun idea. So it builds upon two ideas. The first one is skip lists. And so anyone who's ever worked a course in data structures knows what a list is, and knows that if we are to keep a linked list sorted, in order to find any element, there's no shortcuts. You have to start from the beginning. So let's say we're searching for element 21 in this list. We have to do a hop to number 2, hop to number 9, 14, 16, and only at the 5th hop will we get the result. We'll find 21. Okay, skip lists, they build upon this literally by adding layers to this list. So instead of only keeping a single list, we're adding higher layers which have a lower count of elements, so only some of them, and this allows us to quicker search through this list. So now if we want to find element 21, we start off at the highest level, L2. We hop to the value 16, right? We're skipping 2, 9, and 14. After that, we hop to the value 24. And at that point, we see that we've gone too far. We've skipped our value, right? We have to go back and go down a layer. We repeat this, so from 16, again hop to 24, again return, hop down one more level, and at the base level we finally find 21. Now this is 4 hops, I think, so that's not really, in this example, cool, right? But in reality, it's going down from linear search time to logarithmic search time, and that's massive. Okay, those were skip lists. The next idea is navigable small worlds. So, if we take our vectors and say they are all graph vertices, so we're building a graph where our vectors are vertices, and the edges between vertices are created between the closest vectors, we get a proximity graph. If we are now to take this idea and build upon it a bit further, and that is, instead of only adding edges for nearby vertices, we're also going to add some medium length and some long length edges. Now this is a navigable small world. And what we have with these long edges is, if we pick an entry point for search, a vertex that is an entry point for search, we get a really quick way to go over large parts of this graph in the search. So let's look at an example. We've chosen this vector as an entry point, and we want to find the nearest neighbor to the query vector, okay? So how does it work? We start from the entry point, we calculate the distance from the query. We then look at all of its neighbors and check whether any of the neighbors is closer to the query than our entry point. If such a point exists, we hop to it, and we repeat this process. So we're checking the green vector plus all the neighboring vectors. And so we once again see that there is a neighbor that's closer to the query than us, so we hop there. We repeat this process. We see that there's no better neighbors than us, and that's when we conclude, okay, I'm the nearest neighbors, I'm the result. So this is, again, obviously a greedy algorithm. It's not an exhaustive search, so we will not have 100% accuracy or recall here. And that's an issue with HNSW, especially in higher dimensions. It starts missing a lot. It starts returning local maximums and so on. So it's not really usable in today's world. Okay, and now we combine these two ideas to get HNSW, and practically it's really easy to imagine. We take an NSW, we add layers to it, we add connections to it. This is an hierarchical navigable small world. Now, the same as in skip lists, layer 0 contains all the elements. Layer 1 has fewer elements. They're all repeated. They're all kept redundantly from the 0th layer. And the top layer has the least amount of elements. We will call one of the vectors on the top level the entry point. And once again, when we're trying to do a search, we'll start from that entry point. The algorithm is pretty much the same. You go from the entry point, you check all your neighbors, you see that this point is closer to the query, and then check for that point, you see that there's no better neighbors of that, and then you go down a layer, the same as in skip lists. So now we went down, and now once again, we're repeating this. We're going to search all the neighbors, see that this one is closer, check all of its neighbors, go down since there's no better ones, and in the end, find the best, the closest vector at the base layer. And this is our answer. This is our top one nearest neighbor. So in practice, we're often looking for more than one neighbor, and so there's some parameters that we can tune here about how exhaustive our search is. That is, we could have multiple entry points when entering a layer. That's a parameter we set. So it's always a trade-off between search speed and accuracy, how exhaustive you are. Let's talk for a minute just about how we are building this. This is our most complex index or algorithm to build so far. It's an iterative process, meaning we start off from an empty graph. When we're adding a new point, first we have to decide which layer it will belong to. And yeah, just a note, if we decide to add something to layer 2, we will also add it to layer 1 and layer 0. So you will also always belong to your layer and all the layers below you. If you're only on layer 1, you will be on layer 1 and layer 0 as a point. So when we're building the index and adding a new point, we have to decide which layer it belongs to. There's the highest chance is that you will only belong to layer 0, and the chances of going upwards, they exponentially fall down. So the point is to have really scarce layers at the top, and they will have really long connections, and that's what allows us to quickly traverse this whole data structure, because we can make those long hops in the upper layers and then do finer, more granular searches at the bottom layers. So that's it for HNSW. As I've said, it's the best currently existing and used index. And lastly, I did a little benchmark. It's not really scientific, so please don't hold me responsible for these results. So we're going to be comparing for different index types what the train time is, search time, and how good the recall is. So for a flat index, that's the basic solution. We're not really doing anything during train time, so it's 0 train time. For search time, it takes 4 seconds. This is for 1 million vectors on my PC. And the recall is 100%, right? You're not going to miss anything if you search through everything. Using just PQ to train the index, so to encode everything, keep a codebook and stuff, it takes 4.5 seconds. The search time has stayed the same. That's a little strange to me, but I haven't gone too much in depth. And recall is 0.43. Recall in this context is out of the real top 100 neighbors, how many of them did you get right in your top 100? So PQ gets 43 neighbors right of the top 100. LSH, really short train time. Search time is a bit better, so 2 times less. But the recall is pretty bad, so we're missing a lot of real nearest neighbors. HNSW, now finally we get to a longer search train time, around 37 seconds. We see that the search time is the lowest of all of these, but also the recall is quite good, 0.86. So that's, I would say, good enough for most use cases, especially if you've got a bunch of texts or images. A lot of them will be similar, so the most similar ones aren't always the correct answer, right? And lastly, this is what you're often going to be using in reality if you've got a bunch of vectors and they're all high dimensionality. You're going to be combining HNSW with product quantization, so to really reduce the amount of memory you use for your vectors, but also to lower the amount of time you need to search them. And it took around 50 seconds to train this. Search time is the quickest of them all, and recall is still better than just PQ or just LSH. So if you've got a large-scale problem, this is something you'll probably be using. Or if you've got a really large-scale problem, you'll probably be using a vector database and not really thinking about any of this. This will all be under the hood for you, right? Okay, just to go through this again, or just to keep them on screen, we went through some of these indexes. My name is Dusan Milunovic. I work at SmartCat. Feel free to add me on LinkedIn if you want to discuss anything or talk to me or whatever. We've got some time hopefully left for questions now.
Yes, we have.
Okay. Also feel free to approach me later if you're shy.
Okay.
Okay.
We need a microphone.
Who raised their hand?
A lady first.
Hi, thank you for your talk. So a question about benchmarks. So this was your experiment that you run, or does it reflect, I don't know, some other benchmarks?
It does reflect, although I don't have the numbers in my head. But yeah, practically, there's a bunch of benchmarks right now because there's a bunch of vector databases and they all got their own implementations and stuff. But this is the gist of it. HNSW will always be the quickest, the most precise. So yeah, and this benchmark I used Facebook AI's similarity search library. It's really easy. It's like 15 lines of code per index. So that was just something I did because it took a little time, and I thought it was cool to showcase. Yeah.
Cool. Thank you.
I think that we have another question.
Hi, can you go to the table that you had?
Not right now. Sorry.
All right, that's fine. I remember the numbers. I'm just a little bit confused with the statement that you said that you are confused that the times are 4.4 and 4.2.
Yeah.
Why?
Why am I confused? Or?
Yeah.
Well, because I've talked about the idea of, so when you get your query, you just encode it. That should take a really small amount of time with these already pre-trained clusters, so a really small amount of time. And then when you're calculating similarity, you're not doing anything specific. You're just doing lookups. And that should be consistent time always, right? So it's not much quicker than, let's say, cosine similarity, but you're not multiplying anything. There's, I would say, less mathematical operations there.
Just a quick question. Have you changed anything structurally in your graphs for flat index and PQ? I'm not sure. You have changed.
Okay, so I've played a bit with, so flat index, there's no parameters, right? And PQ, it's got number of centroids and number of segments. And I've played around a bit until I got a decent number for recall, right? Because you could say we have 2 segments and 2 centroids per segment. You would have recall 0.0001, but it would last like 0.1 seconds to search, right? Okay. So I did that like a few times. I've seen that there's a lot of fine-tuning to do there, just decided not to do it.
Okay, thank you.
Thank you. Is that all? Because it's time for our next session. Okay, yes, it is. Thank
you, everyone.
Thank you very much. This is for you.